Welcome to our MEC410 lecture on shaft design within our class of Design of Machine Elements. This is Chapter 12. The reading for this week is to read Chapter 12 in our textbook. We have 3 homework problems for you to do in spreadsheet form. You don't have to create CAD drawings for load, shear, and moment body diagrams. You just hand sketch them, take a scan, and pop it into your spreadsheet. Each problem does include, however, doing the complete shaft design, which includes the specification of the geometry. You have to do free body diagrams, go figure out all the forces. And the key point in this chapter is we want you to learn at each point in the shaft to show the minimum acceptable diameter to be safe from the standpoint of the strength of the shaft, and that's what we're going to teach you here. So chapters 7, 8, 9, 10, and 11 discussed how to specify pulleys and sprockets and gears and how you attach them to shafts. Here in chapter 12 we show you how to design the shaft and put it all together. I found 3 very good useful videos on YouTube. They're all dealing with automobile transmissions, which are by far the best example of how you put together gears and sprockets and bearings on a shaft. They're very useful videos, not because they get into the mechanical design thereof, but it's more they show you how all the parts assemble, and that's a critical aspect, as you're going to see when we start speccing out various shaft diameters. So this will give you a really good hands-on understanding of how the parts will assemble together. So we have to determine the speed, forces, torque, and power in our systems. And what I've done here is puts a sketch of a power system from our textbook, and then in blue font on the bottom we're going to go step by step through how you actually figure out what dimensions you need on the shaft. As usually, we have to determine the speed of the shaft and the power, torque. Usually you'll be given 2 of the 3 variables in any problem, and you calculate the third. And then we have to determine where you're going to put all the components. Fortunately, again, in our homework problems, we do have the notion of the problems tend to define the location for you. If you didn't have that, you might actually be at it all day. And as shown in view AA on the right side, it's very important for you to understand what the direction of the tangential forces is on these components. The radial forces are always going inward. But the tangential force, you got to get the direction right, so when you draw your free body diagram of the forces, you'll know which way to point the arrow. So the key notion here is the idea of an action or a reaction, which of course is straight out of Newton's law. For every action there's an equal opposite reaction. The action force is caused by whichever of the 2 gear elements, in this case it would be the pinion, is the one that's driven by the motor and is transmitting force to the other shaft, or transmitting torque, I should say. So you see the direction of rotation of this pinion is clockwise, which means the tangential force as shown to the gear is going to go to the left. At the same time, the gear has its tangential force, which is equal in magnitude, but the direction is opposite. So if you're trying to understand what's the direction of the tangential force on the pinion, it actually will be going to the right side in this diagram, and then you have to flip the shaft on its side, be able to draw the free body diagram to say which way's up and which way's down. You also typically in these shafts will specify locations of bearings on opposite sides of some type of gear element. What you got is if there's an axial load, as in a bevel gear, you're going to need to make one of those 2 bearings to support the thrust load, or the axial load as it's called, and the other bearing would support only the radial load. if you have two spur gears that are mating together, then when you put the bearings on the shaft that has the spur gear, there is no thrust load, and so you only need bearings to support the radial loads. The other key notion here is that the reactions on the bearings supporting the radial loads are assumed to act at the midpoint of the bearing. As for where they actually act, it's really a distributed load along the bearing, but that's a very tough thing to calculate when you go do a free body diagram. So for simplicity, we just say that the whole load acts at the midpoint of the bearing. So you have to determine the general shape of the shaft, and usually the shaft has got large diameters and small diameters, depending on how much torque needs to be supported. So usually the way it goes is the large sections of the shaft are going to have to support where the torques and moments are largest, and the small sections, small diameters that is, of the shaft are going to support wherever the torques and moments are smallest. So here it's showing you again this idea of reactions and actions. In the bottom there's a plan view. In this case it says here, for example, the input gear P drives gear A. So if gear A is the driven one, that's going to tell you where the tangential load's going to be on that shaft for gear A. In this case, because the pinion, which is not on the shaft, is rotating clockwise, if you were to go to the shaft up on the top, you would actually have a tangential load pointed down as far as your free body diagram goes. Bearings mate to the shaft via a press fit. Typically what happens is the outer diameter of the bearing is pressed into a shoulder of a housing that's outside of the shaft, and then the inner diameter of the bearing is press fit onto a critical diameter on the shaft. Gears, as you recall, and pulleys and sprockets will mate to the shaft via some type of shoulder or some type of hub. And then you have the next problem is that the gear is going to want to move left and right just due to vibration. So what you usually do is have a larger section of the shaft acts as a shoulder so the gear can't go one way, and then the opposite direction it's going to be a slip fit. In order to assemble the gear to the shaft, you're going to put some type of E-ring or C-ring, as we studied in Chapter 11, to keep the gear from moving in the opposite direction. So if you were asked to find the torque on the shaft, you would just take the power and multiply by 63,000 and then divide by the speed, where the speed is in RPM, so pretty simple calculation. And generally speaking, you're going to want to prepare a torque diagram, which is actually pretty simple. And what happens there is you just show where the mechanical power is input to the shaft, and you show how the other mechanical elements use that torque to do work on their loads. If there's only one other mechanical element present, then the torque on that mechanical element, which is the torque out, is going to be the torque in from the motor. Otherwise, the torque gets split up based on the relative diameters of the different pulleys and sprockets and gears that are on the shaft and on the mating shafts. You have to find the forces on the shaft. Here we're showing a review of how to do it for spur gears. The radial forces are always pointing in, and watch that direction on the tangential force. If this was a helical gear or a bevel gear, then you'd have a third force, an axial force, which would push in the direction of the axis of the shaft. And that's shown here in this next slide, where you can see that not only do you, in a bevel gear, do you have axial loads, but the axial loads don't even act along the axis of the shaft. that supports the bevel gear. They're actually offset. And so when you do problems for bevel gears and trying to understand what the loads are, you find that the axial forces from the bevel gears actually produce a moment on the shaft, where the radius of that moment is the distance between the axial load and the centroid, or the center axis of the shaft. Here we're just showing what we had in Chapter 10, which is that the axial force of one gear is actually opposed by the radial force of the other bevel gear. We have to determine the bending force F sub B on the shafts in a chain drive. And here what you got is you have a scenario where we know that the force in the chain drive in the x direction is F sub C times cosine theta, where you can see in the lower right hand corner of the slide we actually have a little triangle drawn for you. F sub C being the tension in the chain on the tight side, and FCX or FCY, which is the direction that points inward towards the shaft, is the tension times the sine of that angle, and you can figure out that angle from the basic geometry that we had for chain drives back in Chapter 7. Now if we have a V-belt drive, it's actually a little more complicated. If you go through the different force equations for the tight side and the slack side of the shaft, and those equations are shown here on the right. If you have C, which is a multiplier, and C is the ratio of the bending force due to the belt divided by the normal force, if you go through that calculation, you see that F sub B is actually 1.5 times the normal force of the V-belt drive. And the normal force of the V-belt drive is just the torque that's transmitted in the V-belt drive divided by the radius, which is shown here as the diameter over 2. And of course, because there's a large pulley and a small pulley, the actual bending force that you have in the shaft for the large pulley, you gotta use in the equation the diameter of the large pulley. If you try to figure out the bending force for the small pulley, you use the diameter of the small pulley when you do your calculation. But the key one is the bending force is 1.5 times the normal force in a V-belt drive. When you get to a flat belt drive, the analysis is actually a lot more complicated, and they even leave it out of the book because I guess they didn't want to take up the space. But the key equation is that the bending force, instead of being 1.5 times the normal force, now it's 2.0 times the normal force. And here's a quick review of helical gears. We have to resolve the radial forces in the normal directions to the shaft. So recall the radial force is the tangential force times tan V sub t, and the axial force, W sub x, is the tangential force times the tangent of psi. And if you look there on the left, you can see our different angles. We have phi sub n, phi sub t, we have the Greek letter psi. Key issue here is you better understand what all these angles are before you start calculating radial force and axial force. The tangential one is the only one that's the easy one to calculate because that's just the torque over the radius of the helical gear. Now we talked all about stress concentrators in Chapter 5, and these Keyseats, which we discussed in Chapter 11, being the area that you machine into the shaft in order to put a key and be able to transmit the torque on the shaft to the torque either on the gear or on the pulley and vice versa. These Keyseats that you machine into the shaft themselves create stress concentrators. And there's two basic varieties. If a key seat is machined in the middle of the shaft, it's called a profile key seat. And then you use a stress concentrator of 2.0 when you calculate what the stress and the effective diameter is of the shaft at that location. If you have a gear or a pulley all the way on the end of the shaft, then you get what's called a sled runner key seat. The idea here being is it's a lot easier to machine the end of the shaft because you can come in from a ball mill, end mill, all the way on the end of the shaft, and instead of making an oval here, you can make a slot essentially. And because there's really only one section that's machined into the shaft and has a discontinuity, we typically use a stress concentrator at the sled runner key seat of only 1.6 instead of 2. Now, we talked about in Chapter 5 about how abrupt changes in diameters cause stress concentrations in the shaft. Well, the shaft is going to be a series of steps where you're always changing diameter. You might change diameter 6 to 8 times along the length of a shaft that has multiple bearings and gears and sprockets on it. So if you have a sharp corner, which is shown in the upper left corner, or sharp fillet, where the radius is 0.03 or less typically, is actually the key dimension. What you really got is a fairly sharp corner, and you're going to, or a sharp fillet as it's called, and you're going to get a stress concentrator KT equal to 2.5. Now, where you actually have to machine in a very small radius is if you're choosing to use that shaft larger section on the right as a shelf in order to support a bearing. So typically you'll take a bearing, slide it in on the left, and press fit it all the way when it butts up against the large diameter, what's shown as D equals 1.5, and you have to go for a sharp corner because otherwise the bearing won't seat correctly. Now, if you don't have that going on and you have the luxury of putting a larger radius as shown in the lower left corner, here it's showing a radius of 0.19, then what you have is what's called a well-rounded fillet, and in that case you use a stress concentrator of 1.5. And so without having that sharp corner on the shaft, what you're going to find when you go through your minimum shaft diameter calculations is you can actually get away with making the shaft diameter of the small one that is a little smaller than if you had a stress concentrator of 2.5. Now, we talked about these retaining grooves in Chapter 11 as being a way that you would keep a mechanical element from moving. Here we're showing a diagram in the lower left corner of some type of gear, or maybe it's a pulley. It's not really clear what it is, but it's the general idea that this mechanical element slips onto the shaft, and in order to keep it moving left or right, you would put a pair of these rings on, and you're actually machining a sharp groove twice into the shaft in order to be able to snap fit on this external ring. Well, what happens is that you have a very sharp discontinuity in the shaft right where putting the ring on, and so there you're going to have to use a stress concentration factor of 3.0 to account for the retaining ring having a very rather sharp fillet radius. Now, keep in mind a couple of things. For one, this KT equals 3.0 stress concentration factor is not applied to torsional shear stress if it's steady in one direction. It's really more there for the reversed bending. And then the second thing, and this is kind of subtle, is that when you calculate your minimum shaft diameter, you're actually calculating the minimum shaft diameter at the base of the ring groove. In other words, it's actually at a slightly smaller diameter than what's shown where the gear slips on. So then what happens is, if you're going to show what the actual diameter of the bulk of the shaft is, you have to typically increase the ring groove value by about 6% to account for that ring groove depth. What you find when you go shop for one of these rings online is they actually tell you exactly the size of the shaft that they're designed for. They tell you that if you want to buy a certain ring, you're buying it for this standard diameter of a shaft, and you're buying it and such that you have to machine an exact diameter of a groove. And you're going to follow the manufacturer's suggestions. But I will tell you that whoever wrote the textbook and had that 1.06 factor in mind had it pretty much spot on, because if you actually go to a website and you measure up or you read what all the groove diameters are and you add 6%, you're going to hit pretty much spot on what the diameters of the shaft are that the rings are sized to. So that 1.06 factor is pretty exact. Now, it was stated in Chapter 5 that the best predictor of failure in ductile materials due to a steady-state shear stress was our distortion energy theorem. And in the distortion energy theory, the design shear stress is computed from the equation tau sub d equal to 0.577 times the ultimate stress divided by the number of safety factors, usually 2, but sometimes use safety factor of 3. And we're going to use this equation when we go and figure out what the minimum shaft diameter should be in the case of direct shear stress in a shaft. That would be a case where there's a constant shear stress, but there's no variance in the torsion, and there's no variance as a function of time in the bending moments. Usually only occurs on the ends of shafts and for fairly short sections. When we take a look at our design for shear stress under cyclical load, the best way to think about it is in the upper left corner you've got your basic shear stress diagram showing what it would be in a static case where the shear stress is maximized in the middle and tends to go to 0 on the outside. But then you got to remember that the shaft is rotating and that the actual shear is not really constant. So if you look at the bottom of the slide where it says visualization of orientation of element for 1 revolution, what you see is that the shaft is going through cycles. And so here you'll have the idea that at top dead center of 0 degrees you have 0 shear, and as the shaft rotates momentarily at 90 degrees of counterclockwise rotation, you're at max shear, and then at 180 degrees, again it's cyclical, it's a constant RPM, the shear goes to 0, and there at 270 degrees of rotation you're at the negative shear max. So what you find is that any particle of the shaft on the outside surface sees a reversal of the direction of the shear stress, and this is actually analogous to when we talked about reverse bending. And as such, we can actually do a calculation. It's going to take us a couple of steps to get through there to figure out, under those conditions, what should the minimum shaft diameter be. Now, a familiar equation here at the top of the slide is that under constant torque, your tau max is just 4/3 of the vertical shear force divided by the cross-sectional areas. But now we also have to worry about stress concentration. And if you have stress concentration, you have to multiply tau max by K sub t times 4V over 3A. We also know from our distortion energy theorem that the endurance strength in shear is S prime n is 0.577 times S prime n, where the first version of the S prime n was calculated from tau max times the number of safety factors that we have. So when we do some rewriting of these various algebraic equations, what we can find is that if we let tau max equal the design stress, we then create an equation that says kt times 4v over 3a is equal to 0.577 s prime n over n. And then we can solve for n, and n equals 0.433 of s prime n times the area divided by the stress concentration divided by the shear. So now that's a pretty useful equation if the goal is to evaluate the design factor. But we can solve for the required area to produce a given design factor if we just rearrange the terms in equation 12-15. And the reason we want to solve for the area is because ultimately we want to solve for the diameter of the shaft. So the area then becomes 2.31 times the stress concentration factor times the vertical shear times the number of safety factor divided by s prime n. And of course, for a solid circle, area A equals pi d squared over 4, where d is the diameter of the circle. And we can do another substitution and wind up with equation 1216, that the diameter is just the square root of 2.94 times k sub t times the vertical shear times n, and divide by s prime n. And this is a pretty useful equation to compute the required diameter for a shaft where a vertical shear force is the only significant loading present. Now, the more general case is shown as shafts in bending and torsion. And that's really what we're going to find for the majority of our calculations for spur gears, for V-belt shivs, for chain sprockets. And the design stress that we use here for parts of the shaft subject to reverse bending is sigma sub d is s prime n over n. And we saw that equation in chapter 5 also. So now it gets a little more complicated, and we're going to show how you design for shafts in repeated and reverse bending stress with steady torsional stress. And if you look here on the left side of the slide, we produce a graph here that shows what's known as the safe zone. And the safe zone for any shaft is where you design the diameter large enough so that when you calculate on the y-axis what the reverse bending stress and divide by the endurance strength, S prime n, and on the x-axis you calculate the torsional shear stress divided by the yield strength in shear, SSY. If you actually plot a point relating to a certain diameter that you chose on the shaft and you find that your point is in that tan area, then that's a good place for you to operate, and that's where you want to be in terms of calculating your diameter. Getting back to a little empiricism again, that curve, which is the circular line going, or circular arc going between the y-axis of 1 and the x-axis 1, generally obeys the equation sigma over s prime n squared plus tau over s sub ys squared equals 1. So essentially it's an arc of a circle. And we can use sys as sy over square root of 3 for our distortion energy theorem and substitute that into the equation, and then we get the one in the lower right corner where we now see, using our safety factor, number of safety factor n, that n times sigma over s prime n squared plus n for shear times square root of 3 over sy squared equals 1. Generally speaking, we're going to let the number of safety factors for bending be the same as for shear in order to simplify that last equation. We can introduce a stress concentration factor for bending in the first term only, because no stress concentration factor is needed for torsional shear because it's assumed to be steady. So substituting Kt in For the prior equation, we get what you see in equation 12-19. And now we're going to show one derivation of how you go figure out what diameter you need to satisfy equation 12-19. The simplest equation, of course, for diameters to solve is just to have a solid circular shaft. And so 1220 is a familiar equation that you had even back in solid mechanics, where the stress due to bending is just the bending moment over the section modulus, S equals pi d cubed over 32. And we also know that the shear is equal to the torque over the polar section modulus. And the polar section modulus is just twice the section modulus. So we can then substitute these equations into equation 1219, and we get equation 1222. Now the nice thing is that n is showing up as a square and s is showing up as a square, and we can factor them out of the equation and get the one that you see on the bottom of this slide. If we just let the section modulus equal to pi d cubed over 32 for a solid circular shaft, now we can take s out of the equation and get 1223, where we have an equation that shows a solution for d, the diameter cubed. And now you got to do a little algebra and move terms around. And what you find is that you get equation 1224, which is a solution for the diameter of a shaft when it has reversed bending and it's got a constant torque. And the key thing about this equation is that first you got to take the square root of the term ktm over s prime n squared plus 3/4 t over sy squared. Then you got to multiply that by 32 times n over pi, and when you're done with all of that, you have to take the cube root. The best way to illustrate the equations we've been discussing is to go through the example problems in the book. And what I'll do here is go through the flow of the problems and the equations, and then I've created a spreadsheet for each of our examples, 12.1, 2, and 3, that are in the book. And where applicable, I'll put snippets of the spreadsheets on the screen so you can understand how we get all the numerical answers here. So in design example 12-1, the problem is to design a shaft shown in the figures below. And we're being told what material to use, which is SAE 114040 OQT 1000 steel. And the shaft is part of the drive for a larger blower system supplying air to a furnace. Gear A receives 200 horsepower from gear P. Gear C delivers the power to gear Q. The shaft rotates at 600 RPM. Diameter A is 20 inches. Diameter of gear C is 10 inches, and we have a pressure angle of 20 degrees. Now, the first thing we have to do in this problem is understand the action and reaction cases. We were told that gear A is receiving 200 horsepower from gear P. So that means that if gear P is driving gear A, we have what's called an action case. In other words, the tangential force that's going to be on gear A, and that's going to create a force on the shaft, is directly caused directionally by the fact that pinion P is driving gear A. And that's why if you look at the rotation of pinion P, it's going clockwise. Its tangential force on pinion P is going down. That means that the shaft receives a force directionally going down. Now the torque is transmitted through the shaft, coming in at gear A, and it goes out at gear Q. Q is driving gear C, and that's actually going to cause a reaction case for the tangential force on the shaft. What happens is that gear Q is rotating clockwise. Gear C is going counterclockwise. Gear Q is applying a tangential load on gear C, where the tangential load is going up. However, gear C is got a reaction tangential force that's going down, and that reaction tangential force, shown as WTC, because it's going down, it also results in a downward force on the shaft, so that the shaft gets two downward forces in this example that bearings B and D have to resist. So here's our input data, just shown in spreadsheet form. Again, B and D are the bearings here, and A and C are the gears. First thing we have to do is analyze the forces shown, and we use our equations for tangential force and radial force. And again, the most important thing is to show the directions of those forces. The radial forces are always going inward on the gears. We have to calculate the vertical forces on the bearing locations, and you see in the lower left corner is our free body diagram. We've got our tangential forces going down, our reactions on the bearing go up. You do your usual solid mechanics equations. Some moments around D is 0, sum of all forces on the shaft. You write a simple algebraic equation. The horizontal forces, you're doing the same thing, but what you got to remember is that the horizontal forces, what we mean by that is not left and right in this picture, because that would be just along the axis of the shaft. When we talk about horizontal forces, it means you're going in and out of the page, and the plus direction of horizontal is into the page. The sum of moments around D is 0. Sum of forces on the shaft is 0. Notice that the forces WRA and WRC are actually going to be in opposite directions, and that falls from the fact, and we'll show you the previous slide over here. You see that WRA shown to the right means when you rotate this picture 90 degrees, you'll see that the force is into the page relative to the shaft, but WRC is in the opposite direction, and that's why when you page to the free body diagram for the horizontal forces in and out of the page, WRA and WRC are acting in opposite directions. And then we get to draw our shear and bending moment diagrams, and these are useful because we are going to need to calculate the moments at different places along the shaft in order to understand the minimum shaft diameters, and in some cases we may have to understand the shear forces. We need to calculate the horizontal shear force in the shaft and the bending moment in the horizontal plane. This allows us to produce the complete shearing force and bending moment diagram shown. So we sum the shearing forces in the beam going left to right from free end A. Then you see the diagram that's produced based off the calculations. We sum the moments in the beam going left to right from free end A, and we get the moment diagram. And here's a snippet of the spreadsheet summarizing what all the forces are, tangential and radial forces on the gears, and also showing how we calculated the upward and inward forces on bearings B and D. An important aspect of this problem is to specify the shape details of the shaft, meaning the fillets and the rounds and whatever rings we have for grooves, because we need to establish the stress concentration factors at each point in the shaft. So going left to right, we have gear A assembled with a profile Keyseat at point A. That will give us a stress concentration factor there of 2.0. Diameter D2 acts as a shoulder that allows us to rest the gear up against. We then move along to radius 2, little R2 shown here. That is a well-rounded fillet radius. And then we need to press fit the bearing at diameter D3, and when we do that we have to have a sharp fillet R3 in order to allow the bearing to seat up against the shoulder created by diameter D4. Now D4 must be big enough to act as a shoulder for bearing B and gear C, but it's not governed by the stress calculations because it's larger than D3 and it's larger than D5, and it can certainly handle the torque and the moment at those locations. We will get more into how you size D4 exactly when we explain Chapter 14 on bearings and details of bearings. When we get to diameter D5, we have a profile Keyseat for gear C to assemble to the shaft, and we're using a retaining ring groove at D5 to keep the gear from moving to the right. Now you could say we should have a retaining ring groove perhaps at gear A to keep it from moving to the left, but in this example they've left that out, probably because they want to show you mathematically the differences in calculations for all the different possibilities of grooves and fillets and key seats. But in reality you would need a ring groove also at gear A to keep it from moving to the left. We're going to calculate diameter D5 in two ways. One way is with the key seat, the second way is with the retaining ring groove, and you're going to get different values of the diameter, minimum diameter D5. D6 is the diameter that we're going to press fit the bearing at D on. Now in that case we will need a sharp fillet R5 in order to allow bearing D to fit correctly and square on up against the shoulder created by diameter D5. The shaft material was proposed in this problem, and here we're just showing how you would actually get the ultimate strength and the yield strength. In this case, in figure A4.2 in the appendix, it's showing a curve of the strength of material versus the temperature, happens 1,000 degrees F, which then yields a yield point of 83 KSI and an ultimate tensile strength of 118 KSI. We have to determine a reliability factor, our friend from Chapter 5. The default is to use 99% reliability, which leads to CR equaling 0.81. We then specify an endurance strength SN using figure 511. In this case, we have a machine shaft with a tensile strength of 118 KSI, which then yields our endurance strength shown here on the shaft. We have to specify a size factor, but clearly we don't yet have an exact number for the shaft diameter, so we have to take a rough estimate. Here we're showing the idea of taking an initial guess at the shaft diameter to get CS for diameter 5. We're assuming it's going to be around 4 inches, which begets CS of 0.75. The way you set these problems up is you guess in your spreadsheet at a value of CS, and once you obtain a rough estimate of the diameter, you go back and use figure 512 one more time, and then you calculate or you estimate an updated value of CS, and that refines the estimate of the shaft diameter. For wrought steel, we're going to use a material coefficient or material factor of 1. We use CST equal to 1.0. Now we're going to step through the shaft at all locations to calculate the shaft using the various formula. We start from the location at gear A on the far left. We have equation 12-24 to calculate the minimum diameter, but because the moment at the free end of that shaft is 0, it actually comes out to be a simpler equation. The KTM over S prime n squared term drops out when you're at location A, and you can see that D1 based solely on the torque calculates out to 1.65 inches. And here's our spreadsheet snippet for calculating diameter D1. You can see all of the constants are dialed in now to the spreadsheet, that the moments X and Y are 0 at the free end of the shaft A. Therefore, the only value we have to consider is the 21,000 inch-pounds of torque. We proceed to point B, where the bending moments in both planes must be summed. We pick the bending moment in the horizontal direction at B is minus 7,640 pound-inches. It's minus 21,000 pound-inches in the vertical plane. And we sum the squares of those two moments to get 22,350 pound-inches being the resultant moment at B. Now diameter D2 at point B requires a well-rounded fillet to blend into diameter D3. For a well-rounded fillet, we use KT equals 1.5, and we plug that value and the moment and the torque into the equation for D2. Our book says that that gives you 3.3 inches, but I did this in Excel and I got 3 inches. And that's shown on this spreadsheet snippet here, where you see that we've calculated D2 using a resultant bending moment and the torque of 21,000 pound-inches with KT equal to 1.5. I got the minimum shaft diameter of D2 is 3 inches, and we'll go with that for the rest of this video. Now the diameter D3 at point B requires a light press fit for bearing B. R3 is a sharp corner that allows the bearing to seat flat against the shoulder for diameter D4. Now the torque and the moment at D3 are the same as the torque and the moment at D2, but now we're going to use KT equals 2.5 for the sharp fillet, and instead of getting 3 inches for our diameter D3 as we got for diameter D2, this time we get a larger value of 3.55 inches, and that's what we use as a minimum diameter to press fit the bearing. Shown here is the calculation for diameter D3, depending on the same moments and torques as what we use for D2. But now we get the larger value for D3. The diameter D5 at point C requires a key and a ring groove to attach gear C. Now point C is that location. It's got the well-rounded fillet to the left. It's got a profile Keyseat at the gear. It's got a retaining ring groove to the right. And we use the well-rounded fillet at this point because we want the design of the bore of the gear to accommodate the large fillet. Usually it means you get a chamfer at both ends of the bore. And the bending moment at C is again the sum squares of the moments of CX and CY. We get 20,780 pound-inches. Diameter D5 at point C requires a key in the ring groove. And when we use our value of KT equal 2.0 for the Keyseat, we get D5 equals 3.22 inches. But now we have to calculate D5 a second time. It's because to the right of C there is no torque, but the ring groove begets a stress concentration factor of 3.0, and there's reverse bending. And when we calculate D5 for a second time, with the moment equal to 0 but KT equals 3, we get 3.68 inches for D5. And now one more complication. That 3.68 inches was at the base of the ring groove, and we have to use our ring groove factor of 6% to calculate the actual larger diameter where the gear is really fit onto, and that gets 3.9 inches. So whenever you have two calculations for minimum shoulder diameter, you have to go with the larger one, and we will go with 3.9 inches therefore for diameter D5. Here's our calculation showing the minimum shaft diameter. We got the 3.68 inches, and then in the bottom row we multiplied by 1.06 to bring 3.68 inches up to 3.9. Again, the torque was 0 here, but that large stress concentration factor of 3 bumped up the value and got us a larger value than what we calculated previously. Now, diameter D6 at point D is for bearing D, and we don't have any moment or torque at the free end of this shaft. The reason is that the torque exits the shaft at gear C, and therefore there's no torque there by the time you get to the free end diameter D6. And being the free end of a shaft, there's no moment there either. But we do have a shear force in X and Y, and we take the resultant sum squares of the X and Y shear forces, and we get 2,078 pounds. And now we use equation 1216 to calculate the diameter for the shaft at this point, which comes out to 1.094 inches. In Chapter 14, we'll be able to explain that you probably will go with a larger diameter of D6 because you're going to need a fairly good sized bearing that can handle a radial load of 2,078 pounds, and that bearing will likely have a bore diameter that's a bigger number than 1.094 inches. And here's our calculation for diameter D6. This time at the bottom we're using shear forces in order to calculate diameter as opposed to torques and moments. When we summarize the diameters, you notice that we have 6 diameters, but only 5 were calculated based on our equations. Diameter D4 must be big enough to act as a shoulder for both bearing B and gear C, which means that it has to be a larger diameter than both D3 and D5. It'll likely be somewhere in the order of 4.25 to 4.5 inches, but the exact selection of that diameter is D4 is going to depend on what bearing that we supply and the details of the hub for the gear that's supplied. We'll get more into that in Chapter 14.